an ME230 production. Group M9 umbrella stand.
So, according to the dictionary, an umbrella is a device consisting of a circular canopy of cloth on a folding metal frame supported by a central rod used as a protection against rain and sometimes the sun. Here, we will be analyzing the stem of a typical mass-produced umbrella. This is a standard umbrella. When collapsed, it is about 13 inches long, weighs just under 0.5 kilograms, and fits in just about any bag. The magic begins when the umbrella opens. The main functional part of the umbrella is the soft fabric at the top, called the canopy. When extended, the fabric gets taut and is what provides protection against the elements. On the underside of the umbrella, we have the handle, which comes in a variety of shapes and sizes. Next, we have the shaft and the runner, which runs along the shaft and holds the metal ribs together. The ribs are what support the canopy when it is fully extended. The main purpose of the stem is to support the canopy above the user's head by acting as a beam element between the handle and the canopy. Its main function is to remain as sturdy as possible, as a floppy umbrella will tend to disappoint and not serve its intended purpose. The umbrella itself should be designed to operate under rough weather conditions. This means excessive wind in the form of a very irregular load. Since rain makes things wet, a very wet environment is also expected. Let's simplify the situation. The handle is assumed to be thoroughly supported by the user, and the main force acting on the umbrella will be the wind. In order to derive an MPI, the stem has been simplified to a cylindrical beam cantilevered at its base, with reaction forces acting on the end. Since the cross-section remains the same, regardless of which direction a force is applied, the change in direction of any wind can be neglected. The first MPI equation was derived from the following deflection equation. The rigidity of the stem is one of the most critical factors in its operation. By using the second moment of inertia of the circular cross-section, we plug it into the deflection equation and solve for R. The goal is to minimize mass, as umbrellas are handheld and must be held upright for extended periods of time due to the nature of their design. Once plugged into the mass equation, we are left with this equation, which we must maximize. The same process applies for our second MPI. The umbrella stem is a slender rod, loaded at either end. This means buckling is an important mode of failure to consider, so we start with this equation. As a mass-produced product, cost is also a relatively important factor in the material selection process, as small cost increases add up quickly. Once again, the second moment of inertia is plugged into the buckling formula and solve for the radius. We can then insert it into a modified cost equation and end up with the following equation to maximize. Coming back to the first equation for a standard 1.3 meter long umbrella with a 0.5 meter radius, we can use the following formula to calculate the maximum force that wind can act on the stem. From historical weather data gathered in Waterloo, the maximum wind experienced since 1994 was a 74 km/h breeze. Multiplied by a safety factor of 2 and converted to meters per second, this gives us a value of 1,623.3 newtons, which we will assume to act perpendicularly for deflection and along the axis for buckling. From the assumptions and calculations made, we can find the values for constants in the MPI equations and calculate reference points for each graph. The selection lines can be drawn. After applying MPIs based on applications or manufacturing constraints, we selected materials that were recyclable, water resistant, UV radiation resistant, and could easily be machined and manufactured. This left us with magnesium and a wide variety of aluminum alloys. Magnesium was eliminated since it is generally more reactive than aluminum, and at high temperatures, it is highly flammable! 6061 aluminum was selected as it met all the MPI requirements and is one of the most common aluminum alloys in the industry. In order to strain harden 6061 aluminum with a silicon composition of 0.61%, we must first heat the stem in a furnace up to 600 degrees Celsius for 1 hour until the alloy is in the alpha phase. This is followed by immediate quenching to freeze the structure in this phase. We then raise the temperature of this material up to 204 degrees Celsius and hold it there for 1 hour to reach peak aging.
Unfortunately, higher yield strengths cannot be obtained realistically since the longer transformation time is not feasible for large scales of products, which will bottleneck the manufacturing process.
In addition to the naturally formed passivation layer, we have opted to anodize the aluminum to provide a much thicker Al2O3 coating for the aluminum stem, further protecting the stem from the elements and corrosion. In order to meet the harsh environments and high forces it is subject to while still being light enough to carry comfortably and cheap enough to produce, the umbrella stem will be made of 6061 aluminum, a rigid alloy that will be further strengthened by aging and will be given a protective coating through anodization.
Thanks for listening to our presentation. This project was brought to you by Kareem, Justin, and Pascal. Thank you.